like to talk with you today about how to handle a large amount of events, how to not fail into all the pitfalls that we felt. I wish I can come back in time. I wish that I had this talk yesterday and I come back in time with talk to last year, and I talked to myself, don't do that again and do this some other way. So just a couple words about me. I'm in IT for 15 years. I work in Allegro, which you might know as Outro.cz, which is e-commerce platform, which is quite popular in Poland, in Czech Republic, and in Eastern Europe. And for last year, I'm product owner of Hermes. Hermes is a PubSub tool that we built on top of Kafka, and I would like to talk with you about Hermes, about Kafka, and about events, and how to transfer them between all the systems. Just 2 words about Allegro. Allegro is a company that's based in Poland. There are about 500 people in IT. There are about 50 different teams, independent teams. So they built microservices from 2 years, because 2 years ago we had a technical revolution, and then everything began. Then we decided that we need to switch from monolith to microservices, and we need to have distributed event-based architecture. And then we decided we need to have something to handle all the events. So I would like to focus on this with you today. I don't like the agenda slides, so I changed the name of the agenda for what is important when you want to handle events. First of all, for me, important is to choose a tool. That's the first thing we will focus. Then, to distribute the load. Well, it's quite obvious. It's always obvious that if you have multiple servers, you want to distribute load evenly on every server. But it's not as easy as it might sound. So we will look at the particular tools and how they not manage distribution of the load in a good way. Be reliable. When we think about customers for the events, we might think about different types of customers. We might think about events for the logs. We don't care if we lost some of them. But we also need to think about events from the billing systems, and we need to think what would happen if we lost one single event. Well, usually nothing, but it might happen something really bad if this event was for $1 million. So it would be really bad. Then there's 2 really important numbers when you build a system: throughput and latency. Throughput is really nice number. We always like to show, yeah, my system is really great. It can handle thousands of events per second. Great, but what about latency? We fall in this pitfall, and I will show you how to not fall in this. Security. Well, this is also important when you have different types of customers. If you have events about users, it would be quite important if no one else can read data about users. And what's also important, if you have customers, you need to think ahead customers. You cannot just follow their needs, you need to think what they might need. And I would like to show you how we think ahead our customers. So first of all, how we chose a tool. We decided to use Kafka. For those of you who are not familiar with Kafka, we will look at it, and we will have a brief introduction to Kafka. Kafka is a really nice tool which you might think about just a queue, where you append events to the end from the producers, and you remove all the old events for the particular time. But what is really different with Kafka than with other JMS systems is that it's distributed. If we want to scale our system, we need to think how to put data into multiple servers, into multiple Kafka servers, so we can divide our data in topic into multiple partitions. So we publish one after another to multiple partitions. It has also one other nice thing. We can scale our customers. If we have 3 partitions, we can have 3 different customers that read
events from this partition, because as you see, each consumer can read from one partition or more, as this consumer 1 can read from 2 partitions, but one partition can be read only by one consumer in consumer group. As consumer group, we understand applications. So if we have one application, one microservices that have multiple instances, so those are instances, and this is a microservice. But what would happen if we want to scale out, if we want to add another instance? If we just add it, nothing would happen. Unless we restart a lot of instances, then it can handle some of the data. But if we want to scale the traffic, we need to add another partition. So if you add another partition, the new traffic from to the topic will be distributed evenly to all of the partition. I hope evenly, because it's not always possible, and it's not always as easy as it might look. So we want to have also in Kafka partitions to be reliable and secure. So as you see, we divide partitions into multiple brokers. We have 3 partitions, partition 1, partition 2, partition 0, and we have replicas of those partitions. So each partition is copied to another broker. So we have 2 copies of each partition with Kafka. We can have any number of copies, but it's configurable. We can see later how it's configurable and how it's bad in some configurations. We also decided that Kafka is not enough for us, so we decided to build something on top of Kafka. Kafka has its proprietary protocol, binary protocol, so we decided to use REST as a protocol to post events, and REST as a protocol to post events to consumers. Because of that, it's really easy for us to change communication from synchronous mode, where we have microservice and microservice, to asynchronous mode when we have microservice, Hermes, or Kafka, and microservice, because we need just to change URL of endpoint. So that's the Kafka. Kafka is really easy. So what might happen wrong? We want to distribute load. In the default configuration, partitioning is done by round robin. So we write event in the first partition, the second partition, third partition, then in the first, etc., etc. It's quite easy, but it's actually not the thing that happened in Kafka. In default configuration Kafka, they decided to optimize the number of sockets that they use. So they decided, we have multiple producers, so we can stick single producer to single partition for some time, and some other producers to some other partitions, and math says, okay, it will be okay. But if you try to do it with single producer, you will finish with one single broker that is highly load, and 2 brokers that has not load at all. So that's the one thing that you need to think, that if you think about optimizations that are done in Kafka or in any other event-based systems, they're done for the really distributed environment. If you have single producer, you might finish with the really weird situation. You can also always abandon it by doing key-based partitioning. It is really nice because you can have all the events that are connected to the key that you define in the single partition. It is there's one nice thing about this, because you can read subsequently from the single partition, and you are sure that every event that is after the one that you read, it came after to the Kafka. So it's one nice thing that you need to remember. With Kafka partitions, there's one more thing. If we think about brokers, as I show you before, we have leaders, we have replicas, and we have multiple brokers. If we look at the configuration, we can see that for each topic, we have topic test. For each topic, we have 3 partitions. We have here partition 0, which has replicas 3 and 1. So we can see replica 3 and replica 1. ESR says, okay, both of these replicas have all the data that we want to have. They are in sync. The copy of the leader has all the data that we would expect that they have. And we have elected leader, which is broker number 3. But what would happen if we lost one broker? Let's imagine that we lost broker number 3. We can see that it's lost from the ISR, because it's not in sync anymore, because we don't have broker number 3. It's still in replicas, because we expect broker number 3 to have data on it, but the leader become broker number 1. So it's quite obvious. But what would happen if we bring the broker number 3 to life again? First of all, it needs to gather all the data from broker number 1. So we have load on broker number 1 because we need to copy all the data. But then nothing happened. We see that there's in-sync replicas 1 and 3. Both of them are in sync. We have all the data on broker number 3, but we have highly loaded broker number 1 and not load at all on broker number 3. So there's one more thing you need to remember if you build that system, that it's really hard to distribute load on Kafka and on some other system. It's rather easy in Cassandra and some other systems like this, but in Kafka, there are some tools, but they are not perfect. You can finish on with all the partitions in single broker. So you can finish with, we finished with one broker highly loaded. We cannot handle all the events. We can handle only the half of events that we built our system for, and that was our system, our issue. The second thing that we looked at was to be reliable. What it means to be reliable. For different people, it means different things. You can think about logs when you don't care about them at all, about page views. You just care about statistics. If you lost one event, no one cares. So you can just send them. Okay, it's 0, I don't care. I send it to my pub subsystem, I don't care. You can think about all other systems when you want to have events stored securely. And we thought, okay, if we store them on the master replica, it is enough. It would be asynchronously copied to followers, but not in synchronous mode. So we chose acknowledgement level 1 because it's quite fast and it's quite reliable, quite secure. We run it in our data center, so we were sure that it's not quite often that our servers die. So we can handle it. Okay, if our server dies once every month, we can handle it. And so we choose to go with 1. And then something wrong happened. We saw a lot of issues, a lot of errors on our customers. Our customers said that I want to read data from Kafka in the offset 10,000, but unfortunately there is no data in this offset on Kafka. There's only older data in Kafka. There is only data from 8,000 to 9,000. We just thought, okay, maybe it's our issue. Maybe it's an issue in consumer. Maybe we just did some wrong math or something like this. Maybe, well, something wrong might happen. And then the explanation was horrible for me. Because if you have master and replica, replica is always couple of events behind master. It's obvious. You cannot have the same number of events on the master and the replica. So here, imagine that we have 1,000 events behind master. But there is one strange configuration in Kafka, which is called max lag of messages from master to follower. In our configuration, it was 2,000. So even it was 2,000 less than on the master, we still thought it's in sync. We might turn it off if it was a really small topic, and we would still think that they are in sync. If we had 2,000 events per day, we can turn off our follower for 1 day, and we wouldn't realize that something wrong happened. So, what happened wrong? Servers were still alive because we were sure that they are still alive, but the connection between server and zookeeper were between broker and zookeeper, where broker stores the configuration, was lost just for a couple of seconds. It was just something like network split. It happens. So our follower thought, okay, we don't have leader, so now I'm the leader. And he said to everyone, I'm the leader. That's my current offset. 9,000 is the number of the messages that number of events that I securely stored. You need to follow me. There is one configuration that you can handle to not to follow this issue. There in Kafka it is called enable unclean election, because in this we have unclean election. Actually, broker is not in sync totally, so we need to think, okay, we have some strange situation, not become a leader. We don't have a leader for some time. We have offsite partition, and now we need to choose whether we lose new events. And we can say to our customers, I will lose these events, I cannot save them, or I will lose events that I already said to my customers, I store them. So that's the strange situation. We decided not to follow unclean elections, because I prefer to say to my customers, I won't store these events. It won't happen, rather than, I'm sorry, I lost them. I prefer to say them, it won't happen. But before we think about this, we try to realize what really happens in Kafka. Kafka is really a nice tool, but there's no way to identify event in Kafka. In Kafka, you just put some binary data, and you just get binary data, some events. You can use JSON, because it's quite readable. We use JSON, and we thought, okay, maybe we'll use those JSON and maybe we'll add something. So we decided to add 2 parameters, ID, which is unique ID, and timestamp of events. It's quite usable, which I showed you, which I show you a little later. But with this, we have a little overhead, but we can say, okay, this event is different than event that with the same data that came later. With this, we can handle one more thing, because we didn't trust, before we knew what happened, we didn't trust Kafka, so we decided to use additional trackers. So we put all the identifiers of the events with timestamps to additional tracker. Currently, we are using Elasticsearch. Before we were using MongoDB, and we logged all the delivery items. Because if you are using that kind of massive pops up tool, every time your customers would came to you and say, you are losing my events. If you won't show me that I'm losing my events, then you are losing my events. That's why we decided to build tracker, because our customers didn't trust us. Actually, they were wrong. they were losing their events. It was because of a lot of strange things. But we needed to prove them. If you build that kind of thing, always have some tools to prove that you are not wrong. Because even I read some blog from guys from LinkedIn. They also said it's always Kafka fault. It's never my fault. It's always Kafka. Kafka loses events. And with the normal operation with Kafka, we just pass our events to Kafka. We just save them, and it's everything okay. But in this abnormal situation, like this unclean leader election, or when the brokers are dead, we just implemented some other tool, which we store all the events locally, because we want to be more reliable than Kafka. And we also use it in one particular situation. If Kafka responds slowly. Kafka usually responds fast, but it might respond slowly. In this situation, we want to be quite fair with our customers. So we say, okay, it is not 201, it is 202 HTTP code. I will do my best to store this event, but I don't guarantee you nothing. It might something wrong happen, but I'll do my best. It's not in Kafka yet. When we started with Kafka, I, as a product owner, asked my colleague, do performance tests. How many events we can handle with Kafka? They did it. With the commodity server, it was like 100,000 events per second. It was quite nice. But every one of 10 million events was like 1 second long to save it in Kafka. I asked them what happened. They said, garbage collector or some other stuff, maybe some network latency. Something wrong might happen. Something wrong might happen. But would the whole world stop when you stop? Would the whole world stop when you need to collect your garbage? It's a strange thing, because if you test it, it happened. It happens all the time. If you use Apache Benchmark, Siege, or any other tool, it happens all the time. It is called coordinated omission. It is like your testing tools work tightly with your server and knows, okay, you're not working well, so I won't send to you some new events. But in real life, that won't happen. In real life, if something wrong happens to you, every other people will send you events. There is something worse happen. If something wrong happens to you, they will resend you events. So you'll have more and more events. So if you want to test it really, and if you want to test it in the real life, don't use Apache Benchmark, because it lies. Don't use Siege, because it lies. There is a really nice tool which is called WRK2, which you definitely should try, because it's the only one tool that I know that is not using this coordinated omission way. So it can act like a real word. But it's one strange thing. If you are using Linux, play with configuration flags, because you want build the latest one. There is some strange situation, but you need to play with it. So if we looked at throughput, and it was great. It was like tens of thousands of events per second. But when we looked at latency, which is for my opinion more important, we saw something like this. For the 75% of the events, it is great. It is like 5 milliseconds. I have no questions. It is great. For the 99%, it is like 20 milliseconds. Okay, something wrong might happen. But from 99.9, it was like 45, 60. It was even higher. We had quite a big number of events, so it was like it wasn't the highest number, because the highest number were really high, but 99.9 was like 45 or 40 something. So we thought maybe it is because the message size. If you are handling a lot of events, you might have really strange customers like we had from the search department. They send us 40 kilobytes of event. It's not event anymore. If you are putting all the data that you can gather everywhere, it's not an event. If you are using like couple of kilobytes, it might be an event, but you need to think about this. Think about the size of events. Don't put everything that you might think that would be usable. So we thought, okay, for them, it's also the same as the same graph. But this message size is also 99.9. It's quite huge, but 75% is quite small. So maybe it's because of the message size. No, we tested it with the fixed message size with our test topic, and we had the same situation. So 99 was quite big. So we needed to look further. We needed to investigate further. So we did some more tests, and we looked at the data. Minimum value was great. Median was quite good, but 99.9 was poor. And still, with this test, we had like 60,000 events per second. Actually, it was lies. So we looked at Kafka internals, and Kafka is great. Kafka is fast only because it cheats a lot, because it cheats with the Java unsafe. So it uses it uses Java to write straight to the memory and straight to the disk. In kernel 3.2, there is an error with there are some issues with dirty page PD flash with the tool that flash all the dirty pages to the disks. It should be asynchronous, but in the 99.9%, it ran and it was synchronous, so it stopped all the writes. If we won't look at the latency, we won't look at it at all. If you look only at throughput, you will miss that issues. We upgraded to kernel 3.8, and it's like a huge improvement in this situation. So you need to look at the median. So it's like from 35 milliseconds to 1 millisecond. So it's huge. We can still see some issues, but we need to investigate them further. We can still see, if you won't look at the 99.9, it is great. It's 10 milliseconds, but you need to look here, not on the throughput. When we looked at this, there was the one situation that I omitted. It was the message size. On the old topics, it was like small size. It was like 99.9%. It was like a couple of kilobytes. But we had those topics from the search engine, so it was like 40 kilobytes and more. And they tend to rebuild their systems every night. So they tend to send batches of events every night. So they flooded us every night. So we thought that, okay, we need to optimize it somehow. The first idea was our idea was to use JSON, because JSON is quite obvious. JSON is readable. We can look at Kafka, we can read it. We don't do it at all, but we can. It has big memory footprint. It has also one really bad thing. It has poor support for Hadoop. We store all the events in Hadoop, and then we need to do some get JSON object in every Hadoop query. For me, it's not a big deal, but for the business analytics, it's pain. So we thought, okay, let's do something else. So we looked at Snappy. Snappy is a default protocol of the default protocol in Kafka. But actually, again, in a large amount of events, every one for 100 million events was corrupted. And when it was corrupted, we had a situation where all the partition was stopped, because consumer tried to read something, check CRC, and so, oh, something wrong happened. I cannot read it. I don't know what happened. I need person, I need the operator to do something. And actually, this is what the guys from Kafka told us. You know, just skip it. Just move to another one. We did it twice, and then we thought, no, Snappy is not for us. And there is one more tool, which is LZ4. It is new compression algorithm in Kafka. It is not in documentation yet, but it is in code. So we thought, okay, let's use it. And we tested it. It was great. It was like ratio was 5, 1 to 5, great. 20% of storage we need for this. But we again did really bad thing. We tested it on the same data each time. So as you can imagine, same data compress really great. If we tested it on the real life, it wasn't so good. On the single topic, it was like 10% of optimization. In multiple topics, it was like 10% of overhead. So we decided not to go with LZ4. And then we thought, okay, let's do something else. Let's go with Avro. Avro it was obvious. If I was me 1 year ago, I would told me, go with Avro. Don't look at JSON. And Avro is really nice tool. We are using it right now in some subset of topics. It's Hadoop friendly. It's really fast to verify schema. If you compare it to schema verification in JSON, it's like 1,000 of time that is need to verify schema in Avro. So it's really fast, really nice, and it's also small because it's binary, and it has schema, and it's a really nice tool. So right now we are switching to Avro, and we are optimizing it. What is also important with latency, we tend to thought about latency throughput of the system, but it's also important about latency of the whole system. In Kafka, it is called Kafka offset lag. In Kafka, it is a Kafka offset monitor, which is a really nice tool. It's upgraded right now, so you can use it with the newest Kafka. And it tells us how many events behind the head are the consumers, because it is important for us. Because if there are too many events behind us, we can lose a lot of events because they cannot read it. One more thing is, when we build those systems and we want to handle those events, was to make them secure. Because when we came to people from the user department, from the finance department, they told us, okay, we can store it, but only we can read those data, only we can manipulate those data, we can know what would happen with it. And Kafka, there are some issues. In the current versions, there are no security at all. You just, it's open host. You just publish it. Anyone can publish on your topic. Anyone can read from your topic. There are nothing at all. In the new Kafka, which I hope will be published this year, we'll be kind of Linux-based users, and we'll be kind of ACLs based on the topics. So you can have permissions for read, writes, administrations, etc. But for us, we cannot wait for this, so we decided to build it somehow else. In Kafka topics and in some other tools, topics has flat structure, so you have just the name of the topic. So here I have just the name of the topic. We thought, okay, let's build it the same way as Java packages are. So let's build group as a package, and let's build topic. So with this, we decided, okay, you can do whatever you want with your group. You can decide who can read events from your topic. Because if you publish some secret data like user balance or some changes in user data, you don't want everyone to read it. So we decided, okay, everyone can read it. Not everyone. You decided who can read it. You create it, and we create the group. Okay, and the last thing was when we built it, we thought, okay, we just build the system and put it in our ecosystem, and it would be great. Everyone would use it, and everyone would use it in the proper way. And actually, it won't happen. It won't happen anytime at all. So the first thing was, a lot of people think that you can have exactly once delivery. If you talk to guys from some big companies that want to sell you ESB, JMS, those really expensive stuff, they will tell you, yeah, of course, distributed transactions are our friends. We can have exactly once delivery. We can do whatever you want. You can't. If you want to handle a really large amount of data, you can't have. And there's a really nice blog where you can read why it is not possible. It is not possible. So we decided, okay, you can have only, you can have three options. At most once, exactly once, at least once. So exactly once is not possible. At most once is kind of silly. And so we decided to use at least once. And then we had the problems with our customers, because we tried to send an event to our consumer, and if something wrong happened, we tried to resend it again. And our consumers said, well, do me a favor. If I say I cannot handle this event, I won't be able to handle this event for 1 minute more, because I don't know what happens. We needed to think ahead them. It's not like they can handle all the events, all the issues they have. You need to build a system that is kind of issue-proof for every other systems, if you build that kind of central systems. Because of that, we changed slightly the way that there are events sent from Kafka. In Kafka, you have only committed events, committed offsets. So those are the events on the left are the old events, and all the events that are on the left from the committed offset are the events that I, as a consumer, read, and I know that I read. But in the events, sometimes there are some strange events, like some issues, some events that need to be handled for more than 1 second, etc. So in our situation, we had the situation where this event was handled, this handled, but those white wasn't handled. So we can do it in the two ways. We can wait it for all of them on the single event, or we can just send events, okay, when you can handle it, we will mark it, and we will sweep these events that was already read. We decided to store all the unhandled events in our internal queue, just to be sure that if a customer says, okay, I'm not available, I can send it again. I just check TTL, time to leave, and I send it again and again and again. I tried it with one of the teams. Then guys told me, well, Chris, please don't send 1,000 the same events per second, because I won't handle it. Wait 1 minute, then resend. So that's the optimization that we need to involve. The one more thing was, if you are familiar with TCP, in TCP there's this backoff mechanism. The backoff mechanism says, okay, if you are not able to handle packets, I won't send you all the amount of packets. I will lower the amount of packets that I'm sending to you. We are doing the same. We thought it would be nice. because with that we are adapting to the number of instances that currently run in the customer ecosystem. So if you add some instance, we try to send you slightly more events. If you can handle it, you are sending 503 or network unreachable or something else, we are lowering till we are sending 1 per second, because, well, we are just probing. And then if you add that, we are just sending 1 per minute. And it's like, okay, maybe you will come to life again, but I don't believe it. But we are still trying. And because of the date, we are also implemented the turn back of the time. In Kafka, you can shift offsets. You can say, okay, I want to read, I'm on the offset 1000. I want to read all the events that are in Kafka again. Okay, it's no problem. But you don't know the timestamps of the events. So that's why we added timestamps of the events to each event. And if one of the customers says, okay, I want to have all the events from the last 8 hours resent to me, okay, no problem. I thought it would be unusable. It's used much more than I thought. I would like to show you also Hermes and Kafka a lot. I'm from Allegro, so those are the credentials from Allegro. But let's look at Hermes a bit. So Hermes is available on GitHub. On GitHub is also Docker files, but they are also in Docker Hub. So let's look what's here. We have here Docker Compose. We have here all the tools that are needed to have when you are using Kafka and Docker. So we have Zookeeper, we have Kafka, Graphite, just to have some monitoring. We have endpoint for the senders, endpoint for the consumers, and just a tool to manage all the stuff. So let's run it. If you are using Docker with Kafka, you need to know that if you try to run Kafka before Zookeeper, it will fail, and you need to restart it. It will just disappear. So let's look at what we have here. No, not this version. Okay, let's use this one. So let's use Postman. So let's see whether we have some groups here. No, I don't have any groups. So let's add a group. I called it cz.geekon. Okay, I have my group. I have my group cz.geekon. Let's see the topics. I don't have any topic. So let's add a test topic 1. So I can, yeah, I have, let's see it. Okay, I have test topic 1. So test topic 1. Oh, missing group. It's quite, oh yeah. I have cz.geekon test topic 1 just to test something. I can modify it. As I showed you, in Kafka, you have retention time, the time after which we will remove all the events from Kafka. It doesn't matter whether you read it or not as a customer, we will remove it. So let's change it to 2 days. Okay, I changed it. And let's try to send something to Hermes. Oh, and something wrong happened. Timeout, async timeout. It happened because if you are using Kafka, you usually, first of all, connect to Kafka, gather all the metadata, gather all the information about topics, about all the stuff, and then you try to send. In Hermes, we are waiting 65 milliseconds for this, and it hadn't happened. So, okay, I can send it again, and it's 201. I can see that I have my Hermes message ID, etc., etc. So I can also do one more thing with Kafka. You can have a nice tool which is called Kafka Cat. It is like cat, but for Kafka. So let's see where we have our Kafka. It is on 1992. Let's see whether I'm able to read something from it. It would be interesting. Let's see. Let's read something from Kafka Cat, from my broker, from my topic. GeeCon test topic 1. Oh, I cannot read it. It's because I use Docker Compose and I set from the Kafka. Okay, I'm using it on the virtual machine, and on the virtual machine I have Docker, so I exposed only Docker on virtual machine IPs. I cannot reach it from this. But let's see whether we can do something else. I have here also request bin. Okay, let's run it. Okay, I run just request bin. Okay, I can create one of them. Let's use it. And I can create a subscription for my topic, which is says that GeeCon test topic subscriptions. And if I add it, okay, it is created. I can send any topic, any message to this topic, and it will be, I hope, send it. Oh, and it is sent it to request bin. If you, as you saw, all the old messages wasn't sent because it was already in the queue when I joined it. By default, when I joined it, I start reading from the end. So I hope that you will play with Kafka. I hope that you will play with Hermes, because Hermes is quite nice tool built on top of Kafka. It's open source. You can just download it from GitHub. You can use Docker. So play with Kafka, build pops up, handle large amounts of events on your own. Thank you.
Any questions? Sorry.
So if you have any, there are some, okay. Okay, there are some.
Okay, so when you were talking about compression, like how many frameworks did you actually check? Like, did you try protobufs on or Cap and Proto, etc.? And do you have it somewhere posted? Like, how exactly did you do it, and what were the results?
Okay, so how many protocols did we test? If you are thinking about Kafka, they have its own protocol and its own compression. So I was talking about compression between Hermes and Kafka. So we had just to use Kafka protocol with Snappy and LZ4. But we tested in front of Hermes, we tested, actually we are switching to HTTP2, just to optimize, and we are switching to Avro. We tested protobuf in our former projects. We tested Thrift in our former projects. From our perspective, Thrift in binary was slightly better in our case. But in this case, we are shifting to HTTP2 and Avro. I didn't mention it. I forgot. Thank you for your question.
I want to ask, why did you move from Mongo to Elasticsearch you mentioned in the beginning?
There are a couple of things. Mongo wasn't maintained by us, by our team. It was maintained by some other team, and they had some performance issues those time because everyone wanted to use Mongo, and because that was something like just search whether give me all the maybe not events connected to this event, but give me all the information connected to this event, and it's rather like searching documents for us. Mongo was our first choice, and it was good till some amount of events that we wanted to store it. We had some issues with batch storing data in Mongo. We waited, it was like a couple of seconds for each batch, but maybe it was because of some bigger performance issues we had in our Mongo cluster. So that's why we decided to shift to Elasticsearch, which we knew is quite stable and was right for us.
I have a question. You talk about the rebalancing issues with the leaders.
Excuse me, could you repeat?
You talk about a rebalancing issue with the leaders.
Rebalancing. Yep.
Is it due to Zookeeper, or is it an issue with Kafka?
It is issue with Kafka. The rebalancing is issue with Kafka. Right now in Kafka, the newest Kafka 0.82, there are improved rebalancing, auto rebalancing. Every time broker joins or leaves cluster, it is rebalancing, but it's still you can finish with like 60% on one broker, 40% on second, and 0% on the third one. It is improved, but there are still some issues. It's slightly better than in older version, but it's still issue with brokers. Okay, thank you all for joining me here. Thank you all for the questions. Have a nice day, have a nice conference.